Very good. So it's 7:30 p.m. Tuesday afternoon. Welcome everyone to this evening session of the Maths Meets Art Festival. Today we are focusing on Maths Meets Music. So we had a first event today at 1:15. Just a kind of a brief, very quick overview of what we try to do in this project in terms of mathematics, arts, and music. What are the main goals? If you missed that and you would like to go back and look at it after, of course, this live event, you're welcome to do that. The video is live on Twitch. So today, this evening, we will focus mostly on two projects. The first one will be the sounds of soap films. We'll find out what that means in a few minutes, don't worry. And then the second part will be devoted to the sounds of surface project. Now, before we get started, I just want to remind everyone that if you need any information about this festival, which is running, it started yesterday and it will run until Thursday, any piece of information you need, you can find everything on our website. You can find this link here. Of course, as you may notice, we are streaming live on Twitch, and these videos are recorded. You can access them also afterwards. If you missed something, if you want to repeat something, you're welcome to go there and look at it again. And if you want to engage with us, we really welcome your feedback and your participation. Feel free to do that on Twitch. You can just join and write in the chat. And if you prefer to use a different platform to interact with us, you can also do that on Facebook. We have our webpage on Facebook. And from there, you just need to go to the event page where you can comment and interact with us. Today we have Chloe who will be monitoring these two channels, and she will bring us your questions. So Maths Meets Arts, what is this? So we are a collective of mathematicians and artists, and here we can see some faces, and in particular today, who will be today on the panel will be the ones that I have framed in orange and squares. So I said we have two projects. One is the sound of soap films, and this project is developed by me. You can see me here, and then by Wayne Rossman from Japan and Lee joining us from Leicester. Whereas for the second part of this event, we will have the Sounds of Surface project, which is led by Johnny and Jenny. We'll meet them very soon afterwards. So maybe I will invite just Wayne and Lee to say hello to the audience so that they can see that we are all here. Please, Wayne.
Hello, my name is Wayne. I'm very happy to be here today and part of this discussion, and I'm coming to you from Japan.
And
you've said it all, Alberto. I'm from lockdown South Leicestershire at the moment.
Yeah, but nice to join us online. So great to have everyone on board. So we are ready to start. Now we begin with the sounds of soap films. And for this one, really, I think the best way to start is with Wayne, who will explain what mathematicians understand when we say sound. So Wayne, you can lead from here.
Okay, I'd like to start with a little bit of a description about strings first. Can you see this whiteboard at the moment?
Yeah, I can see
that. Okay, so we'll talk about soap films later, but first, the simplest case of what we're looking at is a string with two fixed endpoints. So here we have a string like on a guitar or a violin or inside a piano, and when it's plucked, it makes a motion. And maybe it moves up and down. So it comes up and then goes down, it goes back and forth like this. And this would be the bass tone, the bass motion of the string. And say if this were, for example, if this was on the x-axis of the real line, and this is where x was 0, and this is where x is pi, then this curve would look like sine x. roughly like sine x. Of course, it's depending on time as well, so there's another variable involved, so that's a bit oversimplified, but just to understand the shape of the curve, you can think of sine x. But also, there's overtones. So for example, you could have a bit of a motion like this, coming up here, staying fixed here, and then coming down here. And then at a different time, it would move to down here and up here and move like this. And this is the first overtone. Which looks like a sine curve again, but it's flowing up and down twice as fast. So it looks like sine 2x. And the way you could emphasize this first overtone, if you're plucking a guitar string and you touch this point with your finger, you don't push it down onto the fretboard, you just touch it, then it will cause this first overtone to come out without the bass tone. And of course, you can continue doing this. You have a second overtone where it's broken into thirds. Okay. Different color there, blue. So you could break it into thirds and have a motion like this. This would be the second overtone. And that would look like a sine curve, but now going 3 times as fast, up and down as the original bass tone. And you could get this overtone to appear by touching the string at the 1/3 point or the 2/3 point. And so you can see these overtones by touching the string and plucking, by touching in the right place and plucking. And when you don't touch and you just pluck the string, they actually all play together to create a particular quality of sound. And I think, Alberto, you have a video you can show showing these overtones on a guitar string. In this video, there's a strobe being flashed onto the guitar, and you hear the sound of the strobe. So you're going to hear a background sound. But that's just so that we can see the string moving slowly when in fact it's moving very quickly.
Fantastic. So let me just start the video. Please flag it if you can hear it.
That's the bass tone. First overtone. Second overtone.
Yeah, exactly. So these are exactly the tones that we can see them. Maybe we can look at them, and I'll stop the video so that we can repeat them. So this is what happens when you try to pluck a guitar. So you try to play it. If you don't touch the string, as Wayne told us, so what the string will do, it will just go up and down, the whole string from the center, and you can see that. So let's look at this together again. You see, it just goes up and down. That's the only thing it's doing. And now, in the next part, what we can see is that we put a finger in the middle of the string. We don't see the whole guitar, but if we just tap in the middle of the string, we can prevent the string from producing the bass tone, and then the string will only produce the overtone. So this is what you can see. It will have a different shape on the curve. And from here you go. From here you can produce all sorts of tones. And so when we talk about sounds in mathematics, what we understand is exactly this composition of vibrations. We could call them just vibrations of a string. Maybe I can share something else with you. I have some simulations where we can see these a bit more slowly. Let me just open it up. There we go. Let me share this one. So here I have just like created a small program where we can see the basics. So harmonics in 1D. Let me just run the program so we can see what's happening. As Wayne has shown us, the string is attached at the beginning and at the end. And the first harmonic is nothing but like a hill, something that goes up and then goes down. It starts at 0, it goes up in the middle, and then it comes down. And this is the basic. And then, as Wayne has said, the second one, it oscillates twice as fast. It goes up and down, and here we go to 0. And then you can have 2 bumps, and you can have 3 bumps. And these guys, they oscillate at different speed. So let's see how the first one oscillates. You can see it goes up and down, and it does that. But now when you play music on your guitar, you have a composition of them. Now, what is a composition? A composition means that essentially you just add these oscillations on top of each other. So if we try to add the first one and the second one, this is what we get. More of a funky shape, I would say. And then if you can add the first one and the second one, of course, you can add the first one, the second one, and the third one, and get something different. Very good. So these are the baseline. This is the base concept behind sounds, or this is like, I would say, how mathematicians may describe sound. So maybe we can start having maybe a quick chat. Lee, if you want to join us, what do you think of these, and how does this relate to your work?
An interesting question. How does this relate to my work? Well, obviously, I guess there's a few things that have kind of come up through the sort of dialogue that we've had that's been quite interesting, because it's not always just been about pitch and sort of harmonic aspects, but actually something just struck me that was quite interesting, which has only just really occurred to me watching the diagrams. I like so seeing the waveforms move and the way that they interact and affect each other when they're sort of superimposed upon one another. Is this word harmonic and the sort of the nature of harmony and things working in tandem and working together in terms of the waves sort of supporting one another in the sense in the way that they move, so we get this kind of this harmonious action. It would be interesting to see, I don't know, can you simulate a non-harmonic action where the waves don't work together?
Well, this is I cannot reproduce that now, but this is something that it's possible when you have waves that are out of phase. So what does it mean maybe for waves to be out of phase? I have something prepared. It's not exactly reproducing something like playing it like this, but we can do something about it. So let me try to share something and what happens when you have things out of phase. So let me go again back to my simulations. If I can open it.
We spoke about the other day, wasn't it? The sort of phasing.
Exactly. I come to that. So as you in the audience can see, this is very much of a conversation that we are having. So we have some mathematicians. So I haven't said that, so maybe we can say more of the background maybe. So I am a numerical analyst. So in my mathematics, what I do is I do a lot of numerical simulations. As you can see here, when I need to explain something, I try to run a computer program to see what happens. And on the other hand, today in this panel of 3, we have Wayne, who is much of a pure mathematician. Wayne can better describe the level of mathematics he is performing, and Lee is the artist. He is the artist on board. Lee is our percussionist, and he interacts a lot with the vibrations, and he has, as a percussionist, somehow it's almost inevitable to identify with this. But now let me come back to this idea that things can be in phase or out of phase. This is related to a conversation we were having, we had a couple of days ago. So Let me run the simulation and see what I mean by this. So if we look at the screen, we can imagine that our string is oscillating like the first one here on top. So you can see it goes up and down, and then to 0. So this is how it oscillates. Now we can imagine that there could be a second wave on a nearby string or on the same string that does exactly the same thing, because these waves, you can imagine, they're like independent citizens in a city. So if the string is a city, then you can have a lot of independent citizens. Someone looks like this, someone looks like that. It's quite of an inclusive scenario. It allows a lot of people to be on the same spot. And so we can imagine we have this one and this one, and when they are together, they're big friends, everything goes well. You see, you just add them up to try to understand what kind of sound you get, and it looks like a very nice curve. To see that I have added these things up, if we look at this point here, this is looks like 1. Now here it looks like this reaches 1, this hill, and this one also. And if you do 1 plus 1 is still 2. Today is still 2, so we get this thing, and it's fine. But now what could happen when we talk about out of phase or things not being so much in harmony or stuff like this, is that one harmonic or one vibration can be shifted. Now I had no way to stop this in the middle, so we will have to watch this maybe twice to see what happens. But let me just run it. So what I'm doing is I'm pulling this vibration to the left. Imagine I'm just shifting one of the strings. And then something strange happens when I sound them up. Let's look at it again together. So now that you see that this one is just moving to the left, so this is becoming out of phase with the first one. Now when you add them up, you can look at the shape of this, and then the shape of this resulting wave is not, it becomes different. So if you look at it, you see it kind of changed shape, and at a certain point, it gets to 0. Now getting to 0, it's quite interesting. It's quite an interesting thing. So it means you have two sounds, you have two citizens in this city, in the string city, and when you add them up, the result is 0. So the implication of this thing is that you're not hearing anything. So you can have the best player, the best bass player on the left, the best bass player on the right, and if they're out of phase, you're right in the middle, you don't hear anything. So this is something that can happen, and we were discussing this thing, Lee, I think it was in terms of microphones, right?
With phasing?
Yeah.
Yes, absolutely. Yeah. So it was funny. I was doing a little bit of swatting up today on this very subject, and I found a diagram which was almost, well, wasn't as sort of beautifully animated as yours, but this notion that essentially the harmonics are bolstering one another, and there's a few instances where this happens in audio. For instance, if you have a pair of speakers and you put them together. I didn't know this in terms of like using like public address systems with speakers, but they actually, you don't get the sum of the two speakers. You get the sum of the two speakers plus a little bit extra, because they're actually reinforcing one another, which is quite interesting. So, but yeah, the thing with the phasing with microphones, you know, you need to get particularly using stereo. So, for instance. Let's think of a good example. When you're setting up speakers in your house, for instance, if you've got a couple of hi-fi speakers, you could probably notice that if you set them, for instance, dead parallel, facing straight at you, that there's a certain sweet spot in the space where you will get a wonderful stereo, and it's a wonderful kind of phased, in phase, comfortable listening experience. But then something to experiment with if you sort of angle them sort of away from one another, or even move to a different point in the room, you'll find that all the bottom end, all the strength of the sound just disappears. And that's when you're either standing in a position, or you've placed the speakers in a position where they're out of phase with one another. So that's from the listening experience, but from a recording experience and capturing these sounds, often one of the sort of practical methods that we can use in the studio is to actually record using two microphones. So what we're trying to do is actually generate as close a capture of maybe, even if it's one instrument, perhaps you say it's a trumpet or a violin or whatever, but capturing that sound in a way that sounds like how we hear it, because without stating the obvious, we have two ears, we don't have one ear in the middle of the head. So we want to try and create this sound it tends to be in a natural, pleasing way. And so consequently, I think we talked about this idea of using stereo pairs of microphones. Quite often is a good system. I think Neumann have actually brought out this it's actually a three-dimensional head. I don't know if you've seen that one with the little microphones in the ears. So the idea is that actually generates a sort of a synthetic listening experience with the microphone placements, which take into account the acoustic properties of a head.
Oh, nice.
So that you really get a sense of exactly what something actually sounds like electronically or synthetically, as sound actually travels to the ears.
Wow. So,
by the way, a similar set of issues occurs when you're building an acoustic instrument. You don't want things out of phase. You want the sounds that the instrument itself, even though it's playing one note, it's creating a lot of sounds. It's creating harmonics, and you don't want them out of phase. You want them to blend nicely, so you have the same set of issues.
I think it's been. I remember a guitar player. Who was it? I can't think now. But he was talking about choosing top range guitars, and he would often sort of tap the neck and tap the body and find an interval, so either unison, octave, fifth, whatever sort of nice harmonic relationships, and that would often be the instrument you'd pick up, and it's singing to itself already. Really, I don't want to sound like the guy out of Spinal Tap, but the notion that you hit the note and the instrument is helping you. Like you say, the instrument designs. Right. When an instrument resonates naturally itself, it feeds the player. It makes it so much easier to play. Yeah. Certainly from a drum context. Yeah. I have a particular tom-tom on my drum kit, which is a beast when I record it, unfortunately, because it has a massive spike at 140 hertz. I know exactly where it is. Whenever I take that into any space, that frequency is going to be the one that it's going to dish out more than the other one, so you have to duck that. And it's a good trick with acoustic instruments, actually, if you can put them in an environment where you can analyze the sort of spectrum of frequencies that instrument is putting out, is that if you're using good quality microphones and they're close enough to the instrument, so not taking in too much of the room account, but just the instrument itself, you can learn a lot about the equalization of that individual instrument and where its hotspots are. So those are the sort of frequencies that if we're recording or if we're using it live, that we would reduce so that it's not disproportionately strong in one place than another. Yeah,
it sounds like you're really taking care of these things when you go and produce music in place. That's the funny thing. The funny thing or the nice thing now is that we mathematicians, we understand these concepts of music or sounds in terms of these vibrations, and then we have a whole mathematical machinery, beautiful mathematics that describes exactly what's happening there. And so it's kind of more like a theoretical approach to that. But then you experience and you learn the same things by just going on site and then playing and sticking a microphone here and try to changing and then analyzing the spectrum. And maybe we should explain this because maybe not everyone knows what is the spectrum. So when you are talking about the spectrum here, what we are talking is essentially what you can do is you can put a microphone next to the instrument or next to the sound source. And then what you can do is you can pick out the vibrations. So the different vibrations. So when you hear them in your ear, you hear them all together. And with these microphones and with some computers and some techniques, what you can do is you can unpack them. So you can go from one to many, and just then you can study the proportion of them. So which one is higher, which one is lower, what kind of frequency we have in there. And then from these, you build what it's called the spectrum of the sound, or mathematicians would say the spectrum of the differential operator. You see, the jargon can be quite heavy, but we mean the same thing. And this is something.
Yeah, and Lee had a nice way to say it. So the spectrum is the collection of hotspots, what you called hotspots.
There you go. That's And in fact, so on this note, maybe let me go, because this is, as I said, this is an ongoing conversation we have been having, and we are sharing now the conversation this with you. Lee challenged us. So Lee said, okay, this the vibration stuff sounds very interesting, but now let me come up with something, and then you tell me how you explain it. No. So let me show you what Lee sent us, and then let's see what you think about it. So let me just open the video. We're jumping into this video here. This is one of the many questions I received, or we received. And so what Lee did, he decided, okay, good, I'm a percussionist. So what I do, I'll take my drum, my big drum, I put it on an amplifier, okay, and then I will just start like hitting my drum. It should create some kind of vibrations. So let's try to pick them up with the microphone. And he understood there's a lot of interesting things happening there. So like, let's try to listen to it. There's a feedback. So this was the first challenge. I don't know if you can, yeah, you can see, let me move this. How is the feedback note created? Now, that's not an easy question.
A quick question. So the mic is picking up the sound of the drum and then putting it back into the speaker?
Yes.
Yeah, what's happening? Yeah.
Yeah, that's what's happening. So you can imagine this is like a vicious circle, because the sound is produced by the top of the drum, and then the microphone picks the notes and put them in under the drum, and so there's like a feedback. There's a loop, no? And the interesting thing is that when Lee goes close to the microphone, so before he puts the microphone close to the surface, there's not much of a sound, but then the microphone can pick some residual vibrations that were on the membrane, and go from there. So let's see again if we can do. This was another one with cymbals. So we were here. You can see, so we cannot really hear like a drum, and then he puts the microphone closer, and then some noise pops up. And so what's happening here in a mathematical term? So what Lee is doing essentially is selecting some of the vibrations that live on this surface. So we can see the drum going up and down because it vibrates very quickly, and then the amplitude is quite small. But with this microphone, Lee is like a detective. He goes and he spots some vibrations, and he says, okay, I'll pick you guys, and then he just feeds this back into the loop, and everything gets amplified, and then you get all sorts of sound, of funky effects, I have to say. So let's play this a bit longer, because this was not the only question he asked us. And this is another interesting spot. So this is something that Wayne and when I saw that, it's like, oh, that's quite interesting. I think everyone could hear that if the microphone is more or less on the outer region, then you get some sort of like whoa sound, or like a whale, no, like you're communicating in the sea with a whale from, which is like, I don't know, from the Atlantic to the Pacific or something like that. And then if you put it in the middle, the pitch is very different. Let's listen to it again just quickly. So you see here, it's quite, and then in the middle it becomes very high. And why is it that? Because some of these, these vibrations have a specific pattern on the drum, and there are many. I don't know exactly what is the term for that. Maybe bass modes, where the vibration is the highest in the middle, and by putting the mic exactly in the middle, so you can just select a very, very, very specific subset of the vibration instead of taking a bunch of them in kind of a random manner. You're very selective when you put it in the middle, and this gives a completely different sound. So this is quite interesting, and Lee then went on having a lot of fun with these things, as we can see. There you go.
By the way,
sorry guys, go on.
Just a quick comment. We received a question on Twitch, and it is, can you hear the shape of a drum? And, this is a deep question. Yeah.
That's you want to explain it?
Well, I'll just comment a bit about it. So it's listening to the sounds like we just heard. If you didn't see the video, could you know that the drum is shaped the way it is? That's the question.
Yeah.
And that's definitely very hard to answer.
Yeah.
And
there's certainly something going on. I mean, in terms of resonance and the way that resonance works. I mean, I guess when you have because the bass drum obviously has a drum head that is what we would refer to as the batter head, so the one that's actually been struck, and then it has a resonant head as well, which is at the bottom. So both the heads in an ideal situation are actually resonating in tandem, in parallel. So once again, rather like the waves, they're kind of reinforcing one another. So once you set that airflow moving in the drum, you get this kind of so I don't know what you call it really, sort of a unison compression movement. Now, what I think is kind of quite interesting along the lines, particularly in terms of the shape of drums, not to say there aren't square drums, because famously Roland Riveron, the comedian, had a square one made. But yeah, the question that I would be interested to maybe see whether you've got a response to would be the example of the kettle drum or the timpani, which obviously is sort of basically almost semi-spherical, if you like.
Yeah. So what happened? So what changes there? So what's the difference? Maybe not everyone has in mind what is the difference. So a drum like the one we saw, it's like a cylinder. You look at it, it looks like a cylinder. It's in particular the top and the bottom are parallel to each other, right? So that's just the drum. Now the tympan, it looks I don't know how to explain this. I think like a nut, like a hazelnut maybe.
An egg. If you cut an egg in half.
Or you cut an egg in half, and that's the shape. So you cut it in half, like you take the egg, you take it from the long side first of all, because you can cut it in half. If you tell this to a mathematician, he will just say, "Oh, you cut it this and this and this and this." You ask a question, and we give 10 questions. So you put like this, you cut it like that. You remain with something that looks like a cup. Okay, you just put a membrane on top, and that's a tympan. And then you play it, and it has I would say it has a very smooth sound, doesn't it?
Mm-hmm.
Yeah. So what happens there is the shape there. So what happened is that this lower part of the instrument reflects the waves. So you can imagine that the membrane is vibrating, and these vibrations are transmitted into the air. So they're going everywhere. They're going up, they're going down, going everywhere. Now, the one that go up, you hear them in your ears. The one that go down, they need to go somewhere. So they start traveling, and then they hit the wall, and they hit the wall of your instrument. Now, if you have a cylinder, what they hit when they go down is they hit the lower part. But if you have something which looks like a mug, like a cup, maybe. It's not hitting a membrane, but it's hitting something solid made of wood. And then they reflect back and they interact again with the surface. And this whole cycle of going up and down, up and down, up and down, and then finally getting out of the system, this is what gives now I'm not an expert here, I would say it gives the color to this.
Because that's essentially the one of the main differences is that the idea of a kettle drum or the timpani is that it does actually give you a specific pitch note.
Yeah.
So, you know, the difference to the bass drum, which is, or really kit drums, it's more of a tonality rather than a pitch necessarily. So
exactly. So I'm not the expert, and as you can see in the audience, this conversation could last forever. It's there's so much to learn and to speak and to exchange. And I know we have a lot of questions on Twitch about this topic, but we need to conclude the first part. So at this point, I would say let's move to the real aim of this project, because I don't know, now time passed and you probably forgot. I almost forgot. This project is called The Sound of Soap Films. No, so we haven't seen soap so far. So where is the soap? Wayne, maybe you can tell something about it. What do we mean? We understand what it means now.
Okay, so we've been talking about strings and surfaces like drums making sounds, and then talking about the collection of hotspots, the spectrum of those instruments, the sounds. And you can do something more abstract. You can take an abstract surface and you can talk about the spectrum, the collection of hotspots, without actually hearing a sound. And so this is part of what we're doing with our research. And I would just like to show this. Can you see it?
Yeah, I can see that.
So this is a collection of soap films. And we can talk about the spectra of these soap films. And as mathematicians, we're interested in this. And here, I'll just make a few comments. You can make all of these physically. You put wire together and to make these shapes, and then you dip the wire into soapy water and pull out the wire, and you get these shapes. And many of them are minimal surfaces. So in the upper left, we see what looks like a rotational surface. As you go up, it rotates. That's called a helicoid, and that's the minimal surface, and that's coming up in a number of days. In fact, it's coming up later today as well. You'll see some more minimal surfaces. I will certainly see them on the last day of this festival as well. And there's some places where we don't actually have minimal surfaces. As soon as there's air trapped inside, the surface bends outward from the pressure of the inside air. And those are not minimal surfaces. Those are called constant mean curvature surfaces.
So you're talking about the one in the middle?
Right in the middle, sure. You see the tetrahedron with a little bit of trapped air in the middle?
Yeah.
The outer surfaces of the trapped air are constant mean curvature, but not minimal. Mm-hmm. And so for all of these surfaces, you can talk about the spectra. And this is something we're interested in.
Oh, that's quite cool. And so by spectra, maybe can you explain what because we talked about the spectrum, so maybe let's be kind and explain what we mean by spectra and how does this relate to sound.
Okay, so if somehow you could bang on these soap films, which we can't actually do, if we could bang on them like they were a drum and get a sound out of them, we would have those hotspots. And the point is to analyze what those hotspots are, even though we don't hear a sound.
Yeah, indeed. And in fact, so we can't hear the sound, but we can look at them at least. So let me share something. This is a video that Wayne has sent me that indicates that, in a certain sense, we should be able to listen to soap bubbles if we are just not there, let's say, but it should be possible. Just to give you an idea of it, this is an experiment Wayne did, I suppose. This looks like a Japanese paper. I'm sharing the screen with everyone. If you can see, there's a video. This is a soap bubble. and this soap bubble is stimulated somehow. I don't know the details of this, but what you can see well here, I'll play it again, is that we have these hotspots. Look at this. Look in the middle. These are vibrations of the soap bubble. And these, from a mathematical perspective, they are remarkably similar to the vibrations of a drum, aren't they? What do you think, Wayne? So that's the same thing.
In fact, this whole experiment is remarkably similar to what Lee just showed us in his video. This soap film is being bombarded with sound from below, just like the speaker below the drum that we saw in these videos.
That is very, very.
So it's really the same thing, but a very miniature version. And the surface of the drum is not a solid surface; it's a soap film.
Where did you do this?
This was an experiment we did in Western Japan about a year ago.
Very nice. Very nice. So the next part, the next video we will want to see won't be tonight, but we will want to see the fantastic shapes that you showed us before, to see how they vibrate and how to get the music out of that.
Yes.
That's I would say this is future work. Let's call it at least. Yeah. It's quite challenging. And so this is this was the first part of this evening. So, but just to give a quick recap, what we try to share with you is how mathematicians understand sound somehow, and how there's a lot of similarities between the mathematics understanding and sound, and what artists do in practice, and from here we have concluded with hopefully some kind of understanding of the sound of soap films. So this part now ends the first part of the evening. We are slightly running out of time, so we'll postpone the Q&A session to the end of the evening. So, and now I think it's time to learn more about the second project. So this is the sounds of surfaces, and for this I'm inviting Johnny to tell us something about it.
Hi there, can you hear me, see me okay?
Yeah, that's fantastic.
Awesome, thanks Alberto. Yeah, interestingly, what we've been doing with sounds of surfaces, almost the opposite of what you guys were showing us there, where you were kind of showing us visually the audio, like the overtones and the sine waves, for example. We're trying to do the opposite and turn the shape of something into a sound. Our shape in question was a Costa surface. We basically used the contours of this Costa surface to get a set of data, basically, which would inform music, which I'll elaborate on that a lot more later on. But we do have a video to play just to show you, sort of, to get a hint of it.
Yeah.
Could you play that, please?
Yeah, I'll play that in a second. Just give me. There we go. So this is about your project, right?
This is the actual Costa surface itself, and a little sort of video we made to describe it and showcase it a little bit.
Okay, so let's enjoy this. This is roughly 2.5 minutes. So everyone sit down and appreciate and enjoy what happened here.
Awesome, thank you. So yeah, that was basically the project, using music that we used for the actual installation. Like I said, before I go into detail about the sort of the tech side and more of that stuff, I just wanted to introduce my partner in crime, Jenny Hibbard. She's just going to go into a bit of background about herself and the project. So over to you, Jenny.
Hi, thank you so much, Johnny. And thanks, Alberto, for showing our video. Cool. So my background, I'm a multidisciplinary artist. I have many endeavors in installation art and all sorts of other realms as well. When I found out about this commission to essentially try and kind of find the intersection or use creativity to explore maths, it was super intriguing, and I've not really felt that connected to maths before, so I was really excited to kind of use art and creativity to really bolster my understanding. So I was trying to think of some ideas, and we went through a creative briefing, which essentially turned into a kind of maths lesson for a few hours, which was really interesting to try and see how Katrin could explain maths to us, to artists who aren't used to talking about maths. So that was a really challenging day, and my brain certainly opened up some new doors. Anyway, so since that day, I thought, and I was really intrigued by the shapes of the minimal surfaces and how amazing they looked. And I put one through, I found some software online where you could turn a 2D image into sound. So I was like, I wonder if you could do the same, but for 3D objects. So I kind of called up Johnny, who I've worked with on a few other projects as well. And I said, hey, can we somehow listen to the shape? and Johnny was like, yeah, there'll definitely be ways to do this. So we discussed how that could happen. And I came with this idea of Sounds of Surface to listen to a 3D shape, which obviously was, well, not obviously, but was apparently very exciting to Katrin, and she chose me as us as one of the 3 projects for the project, which was really cool. So my creative process. So initially I was in meetings with Katrin, and she was trying to explain the surface to me and how it worked, and sent me over her files. So as a mathematician, I found out one studies surfaces with no thickness whatsoever. So in the physical realm, they are impossible. But I think it might make it easier to study, or I don't know. That's one question we can ask later. But basically, so I had to figure out, because I wanted to 3D print the shape so we could have this Costa surface in real life. So I had to learn Blender really quickly. And obviously I didn't learn the entire program, but I added a little bit of thickness to one of the sections. So the Costa surface itself is actually 8 pieces, exactly the same, just kind of 8 symmetries. And I added the thickness, and then went to the hack space, worked with a technician to help me print them on a 3D printer, which formed many challenges, but it was a super interesting process, and I learned a lot. We'll talk about challenges a bit later. And then my next challenge was to create a surface, or a surface for the surface to stand upon. So that was actually another challenge that I'll tell you about later as well. So my process involved kind of 3D printing and laser cutting, and some kind of really delicate and intricate kind of touching up processes on the final 3D print. And also my main idea was to kind of, I really like the idea of it being in the dark. And I think like glow in the dark is always exciting for everyone. And I really like the idea of actually being inside a mathematician's brain and kind of searching around. So we got some UV torches and some UV lights, and I got 3D plastic, PLA, I think it's called, and which is glow in the dark. So we actually printed it glow in the dark. And I love the idea of kind of someone being able to, search inside someone's head, which is pretty exciting. And wrote on these, they're kind of, what's the word? Static whiteboards. So they just roll up and you can just stick them to a wall anywhere, but it doesn't hurt the wall, which was really cool. So that was my process. I'm going to hand back to Johnny, who's my collaborative partner in crime, to describe his process and background.
Awesome, thanks, Jen. So yeah, basically I'm Johnny, aka Andrew Johnston. My background is I have a BA in music technology, a master's in digital art. I'm basically interested in anything that makes noise or is flashy. I do a lot of live audio visuals and installation work. I've done a lot of stuff with Jenny, really. That's how I became involved in the project. She came to me and said, yeah, can you hear a sound? Can you hear a shape? To which I said, of course you can hear a shape somehow. Not really knowing how we would at that time. And then she sort of showed me the Costa service, which we were working on, which I'll show you in a second. So yeah, basically I noticed about, I don't know if many of you probably are aware of Costa services, some people might not be. It's basically, God, how do I explain this? I'm not going to do the inverted sphere thing. It basically looks a bit like an egg timer to the layman. So it's got sort of like a plane that goes this way and a plane that goes that way. Basically, I realised that the contours were sort of smooth and sort of distinct. So basically, if I could find a way to turn that contour data into actual data, we'd have something we could play with. So to do this, I used this little guy. If you can see, can you see? He can see you. That's called a proximity sensor. That basically gives you a distance from itself to the nearest thing to it. So that would be 10 centimeters reading, that would be 5 centimeters, simple as that really. This in turn connects to this little guy, which is an Arduino board, if any of you can read backwards. This, among its many uses, basically I just used as a controller to relay the information from the proximity sensor back into the computer, so it could be used as data basically. I'll show you the thing now. I'm going to switch on a UV light, so it might make the camera go a bit crazy and weird.
Let's look at it.
Where is it? Oh, there it is. Woo! It's gone crazy. So this is the Costa surface itself, looking beautiful. As Jenny said, it's glow in the dark and it maintains its glow as well. I do the hand trick. We used to do the hand trick. We used to do this quite a lot to impress people. It's very visually exciting. I just made a shadow with my hand, basically, put the light on it, and then, oh God, my hand's gone, oh, is the shadow still there? But yeah, visually, aesthetically, it's a really beautiful thing. So how we used it basically was,
Hey, can I just throw in a quick comment?
Yeah, sure.
Yeah, that's actually a minimal surface. You can make that with soap film.
Okay.
Really?
Like in the, yeah,
This
but you can't make the whole thing. You can only make. So you were talking about 8 different pieces, yeah? You could make one of the 8 pieces as a soap film, and then you could stick the soap films together and get exactly that.
Good luck with that.
It would be hard, yes.
Interesting. I quite liked, I mean, the soap shapes that you were showing earlier, just to get a little bit off track. Instead of making them out of soap, surely Lee would be able to construct something and make them out of some kind of membrane, and then you'd be able to hear the shape of the whole thing. I don't know, I just thought about it when I was watching your thing, just to digress. But yeah, we can talk about that in the future. So yeah, effectively, if you imagine the little guy, the proximity sensor is an aeroplane with a radar going across some ground. If it was to, I hope you can see that in the camera, but say if it was going this way, that would be a very low reading because it's very close to the ground. As it would go across, the reading would get much larger as the chasm dipped, and then up a bit, and then down again, and then up to the top. So to give you a sort of like wave like that. The musically among you might recognise that as like an envelope, which it kind of is. It's like a change over time, really. So that's basically how I got the stream of numbers. So like low altitude, high altitude, stream of numbers. We made many passes over the thing in various directions to get many streams of data, which I could then use to change parameters of music. For example, like the left and right stereo field, or the pitch was probably the most pronounced. So to explain, give the example of the pitch, if the proximity sensor was close to the ground, the pitch would be a high pitch, for example, and then when the proximity sensor is further from the ground, it would be a higher pitch. And that's where you get the sort of contours of the sound that you could hopefully hear in the video. Yeah, that was that. I think that's pretty much it, really. So that sort of explains. I don't want to elaborate too much and get into the crazy details, but if anything's confusing or if anyone doesn't have any questions, just go into the Twitch thing and comment on there, and it'll be picked up with an adjudicator. Go on the Facebook group as well. If you don't have a Twitch account, then we can pass it on to the Twitch guys. But yeah, that's pretty much it from me, I guess. So I can just pass you back now to my wonderful projectee, Jenny. She can go through some of the sort of challenges we faced.
Cool.
Jenny?
Yeah, so just to actually go back to what Johnny was saying, like what a Costa surface is, I found out on my journeys through maths that it is a torus, which is better known as a donut, and you take 3 points on the donut and you stretch them to infinity, and that's what a Costa surface is. So if you can imagine an infinite donut, then you're on to an understanding. Okay, so I'm just going to kind of whiz through a few of the challenges I came across, and then I'll pass back to Johnny. Well, actually, we're going to talk about a few, maybe some intentions as well. So yeah, as I was saying about the symmetry of the pieces fitting together, there was a little bit of an issue actually. There was kind of one point which didn't fully connect, and so I had to use a 3D print pen to kind of shove some of the plastic to make it actually fit together. Which is an interesting point, and I'm unsure why that happened. It might have been the way it printed on the bed, or it might actually be to do with the file itself. Who knows? And yeah, so I guess for next time, I think I'd definitely put a lot more energy into figuring out the supports for when I print the 3D prints and tweaking those to make them a little bit like the one side less flat, etc., etc. Also, another thing I realized on the whiteboards, I'd written all of the incredibly complex maths with all sorts of equations and code and stuff. And I think it could be really interesting in the future to try and translate some of that a little bit easier, simpler, so more people could perhaps understand it, which would be really cool. And perhaps even more shapes in the future. But just to, I guess, wrap up the last bit, Johnny, would you like to whiz through a couple of challenges and perhaps an intention, and then we can pass back to the head captain?
Yeah, and now that we have a lot of questions, we have Twitch is on fire, so
wow.
we really need to engage with you. Johnny, here you go. It's you.
Yeah, I mean, the challenges for me weren't great, to be honest. This is a really simple circuit, and there's not a lot that can go wrong. You can use the Arduino for so many different crazy things, and this was, like I said, a really simple application for it. The problems were all in this kind of 3D printing and stuff, from what I can gather, and the kind of manufacture of the shape, stuff like that. But we always smash it out eventually. Stuff in the future I'd definitely like to do is first off, get a much higher resolution proximity sensor so we can get really fine detail of the sort of topography of whatever we're scanning. Also, I want to use them around the outside of the installation to make, not just inform the music, but to make the music somehow as well and affect the music. So it's fully interactive. People are moving around it, and their movements around the shape are also sort of informing the whole installation itself. So yeah, some of the things really, but I'm really happy with how it's gone and looking forward to the future. Back to you, Alberto.
Thank you, everyone. Thank you for showing this very exciting video, exciting project. I have to say, the sound of a journey around a Costa surface is quite a thing. It's quite psychedelic, I'd say. It's and if you start changing surfaces and adding more and more stuff into the equation, the sky is the limit, I have to say. So fantastic project. Thank you for explaining this. And now I think it's time to engage with the public. We have invited people to contribute, and I have to say we are being almost overwhelmed. So Chloe, can you join us here and let us know what are the main questions? What do people want to know?
Hello, Alberto. Hi, everyone.
Hey.
You have quite a few questions. I'm just going to take you back to the first part of your presentation.
Okay.
Somebody talking about harmonics and that they never thought about layering first, second, and third orders is more directed towards Lee. What do you think they would sound like, if they would sound pleasant or not?
Oh, my harmonic knowledge is not great. But if you're if we're looking at going back to very briefly, Alberto's original wave, it was Wayne's wave diagram. So we have one cycle, then another cycle, which is half the distance. So on a guitar, I think we were sort of demonstrating that that's between the bridge and the nut at the top end of the guitar. So the longest length of the string was the first fundamental harmonic, and then the second one is at the 12th fret. Well, that's an octave up, so that's totally as harmonic as it gets. Beyond that, I get a little bit shady. I thought that the other harmonics were half and half again, but we're talking about thirds. So are we in the realms of the well-tempered clavier here? I don't know. Are we into that kind of land? The question's way beyond my pay grade. I'm just playing the drums. You know what I
mean? Wayne, it's on you.
Okay, I guess I would just say every sound does this automatically. There are overtones or harmonics attached to every sound we hear. And so whether they come together to make a nice sound or a not nice sound, well, you can hear it in the sound itself. Yeah.
Good. Chloe, next question.
Thank you. We have somebody saying that it's the sound of a major triad. Not sure if that's correct or not. We also have one more question regarding the drum skin, whether the mic is picking up different order harmonic waves in the drum skin.
So yeah, we planned to show stuff, but we ran out of time, I had to say. So just maybe to comment on this. So as I said, there's different types of harmonics on the drum, and in particular you have two classes of harmonics. So on the string is one-dimensional. You have only one way to oscillate, and on a drum you can oscillate in two ways. Now I will just throw some words. One, you can oscillate radially. So a radial oscillation is, imagine your drum is going up and down and is bumping up and down in a certain way. Now you pick it up, you rotate it a bit, and the way it goes up and down is the same. This is one kind of a radial oscillation. So it doesn't change if you rotate it. And there are other kinds of oscillations where you have, like, you can imagine like a wave going up and down across the boundary of the drum, and this is the second kind. And then you can mix these two things up, and these you can generate two sets of harmonics, higher order harmonics and stuff like that. And the microphone, what the microphone does, it picks a combination of them. It really what really the Microsoft picks up depends on the Microsoft microphone you bought. I'm sorry, not Microsoft. And whether it picks up only, so in particular, the range of harmonics a microphone can pick depends on how you build it. And this is probably not well known, but a microphone is nothing but a drum. So what you have in a microphone is essentially, usually you can have a membrane inside, and this membrane vibrates, and then this vibration is transformed into an electric signal. So essentially what we are doing when we are recording music is we hit a drum, we make something go up and down, and then with another drum we are listening to what's happening. And this is what's in the
that's actually taking us straight to the next question, which is whether is that what happens in our ears, which you just answered, and whether we can explain tinnitus from the science.
Oh, tinnitus. Okay. Mm-hmm. How to explain tinnitus? So tinnitus is when things go a bit wrong in the ear. Is if you party too hard, then you may start hearing a whistle in your ear. I'm not a medic, so I have no competence in that. So don't quote me on this. No. So what the ear does, the ear has a membrane, and the membrane is then capped by a bone, and from this bone, so there's like a bone moving. So a bone is moved because it's attached to a membrane in the ear, and from here we hear this somehow is transformed in kind of signal that our brain can understand. And now I hope I haven't said something outrageous here. So if you're a GP, bear with me. I'm trying to revisit my high school biology knowledge here. Now, when you have tinnitus, is essentially you have damaged something there in the receptors, and this is so what happens when you have tinnitus is you start losing the frequencies you can pick. So this is something that also happens with age. When you have when you're a young boy, fresh, your ear can hear a lot, can hear a very broad range of harmonics, of vibrations, essentially. And now the wiser you get in time, the less you hear, which can also be a sign of being wise. But inevitably, it ends up with the fact that you may not be able to listen to and to hear anyone, which whether it's a good thing or a bad thing, I think I leave this to the audience to decide. But the interesting thing is that what we have been discussing is what's happening in our ears, and it's really there. Thank you.
Great, thank you. Do we have time for one more question?
Yes, one question, yes.
So again, it's mostly directed to Lee. Would love to hear a Costa surface symbol. Has Lee come across anything similar?
We talked about this, didn't we? I seem to remember that it was over a pint.
Yeah.
But yeah, I mean, there's a lot about the surface. I mean, particularly the Costa, the catenoid type shapes that sort of, they almost scream the bell of brass instruments, and yeah, the flared shapes. So there's a sonic thing, and Johnny alluded to the sort of the waveform sort of cross section as well, and there's a lot of things that kind of pull all these things together. I was actually doing a bit of research for a completely different project the other day, and I didn't realize actually that there's a bell manufacturer in Loughborough, which is like 10 miles away from Leicester, not even that, and they cast bells for I mean, check their website. I won't advertise, not like Alberto did with Microsoft a minute ago. but they cast bells, and they can do these things. They do whole sets of bells for churches, this kind of thing. And so, you know, I kind of wonder what a beautiful thing a Costa bell would be. But we also did say that also the bell is one of the most fundamentally simple sonic structures that you can build. So you will get a sound that goes bong, and everyone goes, wow, that's amazing. Do you want to hear it again? Okay. Bong. You can't really do anything with it. So it would be a beautiful object, but you never know. Why not?
What about like a string of minimal surface bells, and then you could just play all of them in an enormous cathedral?
Yeah,
for Christmas.
Yeah.
So we're looking forward to that, Lee. We have a plan now. All right. So I think it's time to wrap it up now, and we are already 10 minutes late. That's great. I mean, it's fantastic. It means people wanted to engage, and we certainly wanted to engage. So this was most of the event. I hope you appreciated it. Now, before closing the browser, I just want to share a few more things with you. So first of all, let me start this so that everyone sees this well. We very, very, very much welcome feedback. So if you liked the event, if you want to share your experience with us, please do that. To do it is quite simple. Just go to our website, and then you click on the top right. You see we have created a feedback page. You go to the feedback page, and then you have a form that you can fill to share your experience with us. And I promise you, this is very short. You know, just 2 pages, less than 5 minutes. There's no snare there, so it's gonna be it's going to be very easy, quick and easy. If you want to spend just 2 minutes on that, that would be amazing. We really very much look forward to hearing from you. Otherwise, this is really the end of today's event. I just want to thank our sponsors here and remind you all the information is on our website. We are live on Twitch. These videos will be made available on Twitch quite soon. And the festival is not over. So tomorrow, next event, 1:15, the arts of the finite topology conjecture, and followed by an evening event, 7:30 p.m., counter deformations, an open rehearsal. And with this is all from this evening event. I really would like to thank you all very, very much. It was a fantastic evening. Thank you so much. And I hope you will join us tomorrow at 1:15 with another very exciting topic, the arts of the finite topology conjecture. Everyone, have a fantastic evening. Bye-bye.